Welcome to our discussion on NP completeness. So you have already seen that we have described the complexity class called P. We also saw the complexity class called NP. Okay. So today we will describe what is it when we say NP completeness. What does it mean? Okay. So before that, we need to understand something called a polynomial time computable function. Okay, so a function f which is going from sigma star to sigma star. Here I will just want to make a point here that what is sigma star. So if you think of sigma, so sigma is what we call as alphabet set. Okay, so typically we said everything will be strings of zeros and ones, so I can think that this is 0 and 1. There are only two alphabets, 0 and 1. Okay, then sigma star is nothing but all possible combinations of 0 and 1. Okay, so sigma star is essentially empty string, then 0, then 1. Okay, empty string is denoted by epsilon, then 0 1. Okay, 1 0 0 0 1 1 0 0 1 0 1 0 1 0 0 and so on. Okay, you keep on doing it forever. That's called sigma star. Okay, so all possible strings you can form with 0 and 1. Okay, so what is this function? So essentially any language L, remember any decision problem we said that you can relate it to a language L, okay, is nothing but a subset of sigma star. Okay, because essentially any problem you see, take all of its instances which are yes instances of the decision problem and look at the encoding of them. They are nothing but strings of zeros and ones. Okay, you take those possible strings, that will give you a language corresponding to that decision problem. Okay, so L definitely is a subset of sigma star. Okay, fine. So what is it we are saying? F is a function from sigma star to sigma star. So if I have sigma star here and sigma star there, f is a function from here to here. Okay, that's f. For every point in sigma star, there is a mapping to another point in sigma star. Okay, fine. Okay, so a function f sigma star to sigma star is a polynomial time computable function if there is some polynomial time algorithm which halts with just fw as output when started on any input w. So if I have a this function is polynomial time computable, that means I have an algorithm which can compute this function value fw given w. Okay, so if there is a value given w, input value given w, it can compute fw, but the time taken to compute this fw is polynomial time. Okay, that's what is called a polynomial time computable function. Okay, so now we will describe something called polynomial time reduction. Okay, or polynomial time reducible. Fine. So we say that a language A is polynomial time reducible to language B if a polynomial time computable function f exists where for every w belonging to A, fw should belong to B. Also for every fw belonging to B, there should be a w belonging to A. Okay, and this particular function is what we call as polynomial time reduction of A to B, and we denote that as A less than equal to with a subscript P B. Okay, that's the notation. Now what it is saying? It is saying that let's say this is my sigma star. Okay, and this is my domain sigma star. Okay, so range. So you have this function going from here. Now your language L or A is nothing but collection of some of these strings. Okay, fine. So what it is saying, if I choose a particular string W from A, FW should be in B. Okay, sorry, that should be FW. Similarly, if I look at any FW in B, I should have some W in A. Okay, so if this is FW in B, I should have the W in A. Okay, so W belongs to A if and only if FW belongs to B. So both needs to hold. Okay, if such a function exists, if this function f exists between sigma star to sigma star, that means it's a polynomial time computable function. Okay, this function should be able to evaluate fw in polynomial time. Okay, and if such a function exists such that if w belongs to A implies that fw belongs to B, and if w belongs to B implies that w belongs to A, then we call this function as polynomial time reduction of A to B. Okay, so that's the definition. So what we are saying is we are going to reduce the language A to language B in polynomial time. That's what it is saying. Okay, so let's understand the basic meaning of this. So first lemma we will state here is that, let's say A is polynomial time reducible to B, and we know that B belongs to P. Okay, that means B is a language which belongs to P. That means it can be, it's a decision problem and it can be computed in polynomial time. Okay, you can get the answer yes or no in polynomial time. Then we can show that A also belongs to P. So how that works? Well, it is simple. It comes directly from the definition. So let's say let M be the polynomial time algorithm deciding B. Okay, so let's say we are having an algorithm M to decide B. Now we already said that M, the algorithm B, since belongs to P, decide means it can say that given any input string, whether it is, for the language B, essentially there is a decision problem. So given any particular string, it will say yes or no. Okay, if the algorithm accepts the particular language, M is that algorithm which accepts the language B, and it can compute in polynomial time. So that's what is the language M we are talking of. So let M be the polynomial time algorithm deciding B, and f be the polynomial time reduction from A to B. Now we said that okay, we will require a function f, and since we said that A is polynomial time reducible to B, that means there exists a function f which can compute in polynomial time given a particular string from A. What is the corresponding string in B? Okay, so f be the polynomial time reduction from A to B. So now we describe a polynomial time algorithm N deciding A as follows. So I have to prove that A belongs to P, which means that I have to give a polynomial time algorithm. Okay, so how am I going to give a polynomial time algorithm? Let's call that algorithm N, and how it works? On input W, this algorithm N works as follows. On input W, what it will do? It will first compute fw. So if I give input W, okay, then it will do what? It will first compute. So recall, we are trying to find an algorithm for A, for this guy, this language. Okay, so what we are saying, first you take an input W. Now since I have this polynomial time function f, okay, just use this polynomial time function f to compute fw. Fw belongs to B, but B is also in polynomial. Okay, B is polynomial time, so B belongs to P, which means that now I can run M, the polynomial time algorithm for B on this input FW and output whatever M outputs. Okay, if this algorithm accepts, I accept. If this algorithm doesn't accept, I reject. Okay, that's the idea. Fine. So graphically, if I put it, let's say, so essentially I am framing this machine N. N is the polynomial time algorithm for the language A. Okay, so you have to take a particular input string, and I will require to say that yes, if W belongs to A in polynomial time, and I should be able to say no, that W doesn't belongs to A in polynomial time. I have to design such an N. Okay, so how are we going to design? As soon as we get W, we know that okay, I can now take this particular W and transform it in polynomial time using this function f to Fw. So this is function f is polynomial time computable function. Okay, so it's going to take polynomial time. Now once I got Fw, Fw is what? Fw is an instance of the language B. Now I run, for language B I have this algorithm called M. So now I run M on Fw. If I get yes, that means Fw belongs to B. Which means what? Which means that W must be belonging to A, right? Because of this particular polynomial time computation, where we said if W belongs to A, that implies Fw belongs to B. So if W belongs to B, which means W belongs to A, right? Okay, so then I will get the answer that yes, W belongs to A. If it is no, then I know that okay, if W doesn't belongs to B, then I know that okay, W also doesn't belongs to A. So I can reject it. Fine. Okay. So what is the total time taken by N? You are spending some polynomial time here followed by some polynomial time here. Summation of two polynomial time algorithm is again polynomial time. Fine. So you got a polynomial time algorithm. Okay. So N is also polynomial time. So now what we will define is called the class NP complete. So language B is called NP complete if it satisfies two properties. Okay, what are the two properties or two conditions? First, the language B is called NP complete if number one, B has to be NP. Now how do you prove something is NP? If you recall, you will prove a language is in NP by using a verifier. Given a particular input instance and a certificate, can you verify it in polynomial time? If you have a polynomial time verifier for that language, you got a problem in NP. So B is in NP. First thing you need to show that. First point. Next you need to show that every problem A in NP is polynomial time reducible to B. Okay. So every problem A in this class NP, every problem is polynomial time reducible to B. I can reduce it in polynomial time to this problem B. Okay. And if I can do that, I will say this particular problem B is NP complete. Okay. Fine. Now let's understand again. What does it mean? That means this is the very interesting part. Essentially what we are trying to categorize is that there are a bunch of problems which are related to each other, and if I can solve one of them, I can solve all of them in polynomial time. Okay, that's what it is saying. So what it is saying, every A in NP, I will look at this NP class, I will pick up any particular problem A in NP, and that problem can be converted to this problem B, or in other words, if I say the language A which is in NP, I know that there is a verifier for it which works in polynomial time given a particular certificate, So I know that it is in NP. I choose any problem in NP, and then there will be a polynomial time reduction to this given problem B. Okay, if then what it is saying is that, okay, what is the intention here? Understand that I took a problem A and I am saying that, okay, and I am trying to judge where is this B, how tough is B compared to all this problem in NP. So I am saying that, okay, I take this problem A, and in polynomial time, that means I am spending some polynomial time and converting this problem A into this problem B. Okay, such that now you understand that if I solve B efficiently, that means if I can solve B in polynomial time, then I will be able to solve my A in polynomial time. Now it is true for every problem in NP. So every problem in NP can be converted to this problem B in polynomial time. Okay, if it is in NP complete, then I just need to have to, essentially, if I can solve B in polynomial time, then I can solve rest of the problems in polynomial time, because given any particular problem, what I will do, I will convert into B. I will solve it in polynomial time, which will give me the solution of it. Okay, so all my problems in NP, suddenly I will be able to solve them in polynomial time. That's great thing. Okay, but we don't know whether we can do that. Okay, but we know that all of these problems are related with each other. Okay, so here comes the first lemma, which I just explained. If B is NP complete, if my language B is NP complete, and if I know that B belongs to P, that means I have a polynomial time algorithm for B, then P is equal to NP. Okay, then I can show that these two classes are same, and it follows from the definition, right? What am I doing? I am saying here is my NP, all the problems in NP. So I choose particular problem. Let's say that's A. I can convert that problem into a problem B, which is in NP. Okay, and I know that, okay, I can solve this B in polynomial time. So all the problems in NP are convertible to B in polynomial time, and I can solve B in polynomial time. That means I can solve all of these problems in polynomial time. So this set will become P, right? Okay, so P is equal to NP. Suddenly this will become true. But up till now we have not been able to figure out any such problem B which belongs to P, also B belongs to NP complete. Okay, if we do that, we have proved P is equal to NP. It is one of the most sought after result in the world. Most people, it's very debatable. Many people believe that P is equal to NP. Many people believe that P is not equal to NP. There are more people, I think, they believe that P is not equal to NP. Okay, so now, having said so, the next lemma says that, okay, if B is NP complete and B is polynomial time reducible to C, yeah, for C in NP, and I know that this problem C is in NP. So I know B is already, I know it is an NP complete problem. Okay, it's a known NP complete problem, let's say. Okay, and now I have a new problem C, and I want to check whether it is NP complete. What is the definition of NP complete? If I have to check that it is NP complete, what all do I need to check? Number one, I need to check that C is in NP. The second part, it says that all the problem in NP should be polynomial time reducible to C. Okay, these are the two different conditions we require to satisfy in order to prove that C is NP complete. Okay, so now what it is saying is, if B is NP complete, if I know a particular problem B is NP complete and B is polynomial time reducible to C, then, and of course C is in NP, then C is NP complete. Okay. So why that is true? Let's look at the proof. So first thing you notice that C is in NP. So in order to prove, what do we want to prove? We prove that C is NP complete. For that, first thing I require C is in NP. That's the first condition. And that condition is true by the statement of the lemma. C is in NP. Okay. So I don't need to prove the first part. Second part, it says that all problems or every problem A in NP is polynomial time reducible to this C. If that happens, then C is NP complete, right? Okay. Now we know that B is NP complete, which means what? That I know that all the problems in NP, definitely they are polynomial time reducible to B, because B is a known NP complete problem. Okay. So once I reduce it to B, now I know also that B is polynomial time reducible to C. So B is polynomial time reducible to C. That means given a particular instance of B, I will use this polynomial computable function f to get an instance of C, which I can solve, right? Okay. So essentially what it is saying is that, okay, all the problems A in NP are polynomial time reducible to C. If I have to prove that, I use the fact that B is NP complete. That means all of this problem A are polynomial time reducible to B. So I will first reduce it to B. And I know also that B is polynomial time reducible to C. So I will then reduce it to C. So I got all the problems A polynomial time reducible to C. So I proved this fact. Okay. So what it is saying is, first of all, notice that C is in NP. So we must show that every problem A in NP is polynomial time reducible to C. Right? That is the second condition. Every problem in A in NP is polynomial time reducible to C. That's what we require to prove. Okay. That's the second part of the condition. Now since B is NP complete, we know that A is polynomial time reducible to B. And since B is polynomial time reducible to C, by the composition of function, A is polynomial time reducible to C. Okay. So essentially now I have shown you that C is also NP complete, right? Now look at again. I have A, this is NP, class of NP, okay? I know that B is NP complete. That means all the problems in A are polynomial time reducible to this problem B. Okay. Also, I know that there is one more problem now, C, and I want to prove that C is NP complete. What we are saying is that, okay, I can reduce from B to C in polynomial time. Okay. Then if I do that, then C is NP complete, because now all these problems are polynomial time reducible to C via B. So first I will reduce it to B, that will take polynomial time. And then from B to C, that will also take polynomial time. So total amount of time spent is still polynomial. Okay. So I will be able to reduce from every problem in NP to C in polynomial time, which satisfies my second condition of NP completeness. Hence, C is NP complete. Okay. Now this lemma tells us something very important. It tells us that I can prove any new problem as NP complete by simply reducing it from a known problem B, which is NP complete. So I have to know at one problem which is NP complete, we have to prove. We don't prove it explicitly for every problem. In order to prove a particular problem is NP complete, what you don't want to show is that every problem in every problem in NP is polynomial time reducible to this problem. That's the definition. But you don't want to do that every time. Rather, use this lemma. You choose a particular NP complete problem. Once you have proved few, okay, or at least one, then you know a well-known NP complete problem. And now your new problem comes and you say, okay, every problem is reducible to this guy in polynomial time. Can I reduce from this guy to this guy in polynomial time? If I can do that, then by composition of function, all of the problems in NP is polynomial time reducible to this guy. And of course, if this guy is in NP, I have proven the fact that this is NP complete. And that's the way to show a particular problem is NP complete. So, if I have to do that, one thing I need to show is that at least there is one NP complete problem, which means that I need one problem at least where I show that every problem in A is polynomial time reducible to this particular problem. Right? Okay, at least I can start with one known problem of NP complete. After that, as soon as I get another problem, I will use a reduction from this known NP complete problem to that problem and use it to prove the fact that all the problems in NP is also polynomial time reducible to B. Okay, and of course, if this new problem is in NP, then this belongs to NP complete. Okay. So we may obtain other NP complete problems by polynomial time reduction from it. So you need to start with at least one NP complete problem. And that's what Cook-Levin proved. And that's the famous Cook-Levin theorem, which says that circuit SAT is NP complete. So if you recall, we discussed what is this circuit SAT problem. You are given a circuit with one single output and you want to figure out, is there a particular satisfiable assignment of all the inputs such that I get one on the output line? That's called the circuit satisfiability problem. We already showed that that problem is in NP. Cook and Levin showed that that problem is just not in NP, it is NP complete. That means all the problem in NP can be polynomial time reducible to circuit SAT. Okay, so that's the Cook-Levin theorem, which we don't want to prove here in this class. It's outside the scope of the class. So, that's the result we will utilize. So what we have shown at least one problem called circuit SAT, which is NP complete. So I hope it is clear what is the definition of NP complete and what is the process to show a particular problem is NP complete. In the next few classes or sessions, we will discuss different examples to show NP completeness. Okay, we will choose few problems and show that those problems are NP complete. So we'll stop at that. Thank you.